Hello everyone, we shall start our course of formal languages, Automata and codes. And today we have language about the closure of regular languages. So we shall start. We have lecture number 11. So here's the following question. Given two languages, L1 and L2, is their union also regular? In specific instance, the answer may be obvious, but here we want to address the problem in general. It is true for all regular L1, L2 languages. It turns out that the answer is yes. A fact we express by feigning that the family of regular languages is closed under union. We can ask similar questions about other types of operation on languages. This leads us to the study of the closure property of languages in general. Closure properties of various language families under different operation are of considerable theoretical interest. At first think, it may not to be clear what practical significance these properties have. Admittedly, some of them have very little, but many results are useful. By giving us insight into the general nature of language families, closure properties help us answer other more practical questions. We shall see instance of this later in this course of lectures. Closure under simple set operations. We begin by looking at the closure of regular languages under the common set operation, such as union and intersections. Theorem. Let L1 and L2 are regular languages, then so are the union of lang1 and 2, the intersection, the product, and the complement of language L2 and L1 star. Here it's misprint, yeah, L1 star. We shall say that the family of regular languages is closed under union, intersection, concatenation, complementation, and star closure. Proof. If L1 and L2 are regular languages, then there exist regular expressions R1 and R2, so that L1 recognized by the expression R1, and similar we have for L2 for the expression R2. By definitions, the sum R1 and R2, the product, and R1 star are a regular expression denoted by the language is the union of L1, L2, the concatenation, L1 and 2, and the L1 star, respectively. Thus, closure under union, concatenation, and star closure is immediate. To show closure under complementation, let M be deterministic finite acceptors that accepts as language L1. Then the deterministic finite acceptor M with hat, where final states are Q without F, except the language which is a complementation of the language L1. This is rather straightforward. We know that in the definition of the deterministic finite acceptor, we assume that the transition function delta star to be a total function, so that the image of delta star of Q0W is defined for all words W from sigma star. Consequently, the delta star of Q0W is a final state, in which case W belongs to L, or delta star of Q0W belongs Q without F, and the word W belongs to L. Demonstrating closure on the intersection takes a little more work. Let L1 is a language determinant accepted by automaton M1, and L2 is a language accepted by automaton M2, where M1 is such deterministic by another chapter, and M2 is the following. We construct from the automaton M1 and M2 combined automaton M with head with the set of states Q with head. Our alphabet sigma similar as alphabet of automaton M1 and 2, and as a transition function delta with head. The initial state is a ordered bars Q0P0, where Q0 is the initial state of automaton M1, and P0 is the initial state of automaton M2. And we have here also a finite final state F with head, whose state Q capital with head is equal as the Cartesian product of Q and P, where Q is set of states of automaton M1, and P is the set of all states of automaton M2. And the state set Q capital head consists of the bar Qi P J, yeah, and whose transition function delta with head is such that automaton M capital with head is in the state Qi P J, and whenever M1 is the state Qi and automaton M2 in the state Pj. This is achieved by taking delta with heart of such state Qi of the symbol A is equal Qk PL, yeah. Whenever delta of 1 of Qia is equal Qk, and delta 2 of Pja is equal PL. Final set of final stars F capital with head is defined as a set of all ordered parts Qi Pj. Here is misprinted, Pj must be an index such that Qi belongs to the set of final states of automaton M1, and Pj belongs to the final states of automaton M2. Then it is a simple matter to show that the word W belongs to the intersection of the word L1, L2, if and only if it is accepted by the automaton M capital with head. Secondly, the intersection of language L1 and 2 is regular. The proof of the closure on the intersection is a good example of the constructive proof. Not only does it establish the desired result, but it is also shows explicitly how to to construct a finite acceptor for the intersection of two regular languages. Constructive proofs occur throughout this course of lectures. They are important because they give us insight into the result and often serve as a starting point for practical algorithms. Here, as in many cases, there are shorter but non-constructive or at least not so obvious constructive arguments. For the closure on the intersection, we start with De Morgan's law, taking the complement of both sides. Then the intersection of the language L1 and L2 is equal the complement of the union of the complement of the language L1 and L2 for any language L1 and L2. Now, if L1 and L2 are regular languages, then by closure are the complementation, so are L1 and so here is print, yeah, must be the complement of L1 and L2. Using closure and the union, we next get the union of the complementation of the language L1 and L2 is a regular language. Using closure and the complementation once more, we see that the following equality holds, and hence the intersection is a regular language. So in this moment, the following example is a variation of the same idea. Example shows that the family of regular languages is closed under difference. In other words, we want to show that if L1 and L2 are regular languages, then the difference of L1 L2 is a necessary regular also. The needed set identity is immediately obvious from the definition of the set difference, namely L1 difference L2 is equal L1 intersection with the complementation of the L2. The fact that L2 is a regular language implies that the complementation of the language L2 is also regular. Then, because of the closure of regular language and the intersection, we know that the L1 intersection of the complementation of L2 is a regular language, and the argument is complete. A variety of other closure properties can be derived directly by elementary arguments. Theorem. The family of regular languages is closed under reversal. Proof. Suppose that L is a regular language. We then construct a non-deterministic finite acceptor with a single final state for it. In the previous lecture, we showed that this is always possible. In the transition graph for this non-deterministic finite acceptor, we make the initial vertex a final vertex. The final vertex is the initial vertex and reverse the direction on all the edges. It is a fairly straightforward method to show that the modified and deterministic acceptor accepts the reverse bars of VR if and only if the original and deterministic finite acceptor accepts the word W. Or the modified deterministic finite acceptor accepts the language, reverse language LR, proving closure at the reversal. This is complete proof, closure, and the other operations. In addition to the standard operation in languages, one can define other operation and investigate closure property for them. There are many such results. We select only two typical ones. Others are explored in the exercise at the end of this section. Suppose sigma and gamma are alphabets, then a function h from sigma star to gamma star is called a homomorphism. In words, a homomorphism is a substitution in which a single letter is replaced with a string. The domain of the function h is extended to the string in an obvious fashion if w is equal a1, a2, so on, an, then h of w is equal h of a1, h of a2, so on, h of an. If L is a language on alphabet sigma, then its homomorphic image is defined as h of L is a set which consists of the h of W, where W is a word from the language L capital. Let sigma consist of two elements, A and B, and gamma consists of three elements, A, B, and C, and define the mapping in the following way. H of A is equal AB, H of B is equal BBC. Then H of ABA is equal ABBBCAB. The homomorphic image of the language L, which consists of AAABA, is the language H of L, which consists of two words ABAB and ABBBCAB. If we have a regular expression R for a language L capital, then a regular expression for H of L capital can be obtained by simply applying the homomorphism to each alphabet sigma symbol of R. Example, take the alphabet sigma consists of two elements A and B, and gamma consists of three elements B, C, and D, and we define the map H homomorphism morphism A by the formula H of A is equal to DBCC and H of B is equal to BDC. If L is a regular language denoted by the following expression R of A plus B star multiply AA star, then R1 is equal D BCC plus BDC star multiply DBCC star. Noted the regular language H of L. The general result of the closure of regular languages and any homomorphism follow from this example in an obvious manner. Theorem: let H be a homomorphism. If L is a regular language, then its homomorphic image H of L is also a regular language. The family of regular languages is therefore closed under arbitrary homomorphisms. Proof: let L be a regular language denoted by some regular expression R. We find H of R by substituting H of A for each symbol A from the alphabet sigma of regular expression R. It can be shown directly by an appeal to the definition of a regular expression that the result is a regular expression. It is it is equality easy to see that the resulting expression denotes h of L. All we need to do is to show that for every word from the language L of R, the corresponding image H of W is in L of HR. So if we have that expression R contains the word W, then we get that the expression H of the image of expression F of R contains the image of the word W, H of W. Yeah, and conversely, that for every word V in which is generated, which lies in the image of the expression R by homomorphism. And there is a word W in the language L, but that V is equal H of W. Leaving the details as in exercise, we claim that the image H of L is regular. Definition. Let L1 and L2 be languages on some alphabets. Then the right quotient of L1 with L2 is defined as L1 quotient right quotient L2 consists of such word X such that the word X, Y belongs L1 for some Y from L2. To form the right quotient of L1 with L2, we take all the strings in L2 that have a suffix belonging to the language L2. Every such string, after removal of this suffix, belongs to the right quotient of L1 with L2. Example. If L1 is a language consists of such the word A in power n, B in power m, where n is a positive integer and m are non-negative integers with the word BA, yeah. And L2 consists of the word of the form B in power m, where m is a positive integer. Then the right quotient of L1 with L2 consists of A in of the word of the form A in power n, B in power m, where n is a positive integer and m is a non-negative integer. The string of the language L2 consists of one or more symbols B. Therefore, we arrive at an answer by removing one or more symbols B from the those string in the language L1. That should terminate with at least one B. We know that here L1, L2, and the quotient, right quotient of L1 with L2 are all regular. This suggests that the right quotient of any two regular languages is also regular. We shall prove this in the next theorem by constructing that take the deterministic finite acceptor for languages L1 and L2 and construct from then a deterministic finite acceptor for the right quotient of L1 with L2. Before we describe the construction in full, let us see how it's applies to this example. We start with the deterministic finite acceptor for the language L1, say the automaton M1 with state, the set of state Q, our alphabet sigma with transaction function delta with initial state Q1 and the final state F capital in the following figure. Since an automaton for the right quotient of L1 with L2 must accept any prefix of the string in the language L1, we shall try to modify the automaton N1 so that it accepted X if there exists any Y which satisfying the formula 1, yeah? The difficulty comes in finding whether there is some y such that xy belongs to the language L2 and y belongs to the language L1 and y belongs to the language L2. To solve it, we determine for each state Q from Q capital whether there exists a walk to a final state labeled by the word V such that V belongs to the language L2. If this is so, any word X such that delta of Q0X is equal Q will be in the right quotients of the language L2 with the language L1 with the language L2, yeah. We modify the automaton according to make Q a final state. To apply this to our present case, we check each state Q0, Q1, Q2, Q3, Q4, Q5 to see whether there exists a walk labeled by the word of the form BB star to any of the states Q1, Q2, or Q4. We see that only Q1 and Q2 quality, Q0, Q3, Q4 do not. The other automaton for the right quotient of language L1 with language L2 is shown in the following figure. Check it to see the construction works. The idea is generalized in the next theorem. Let L1 and L2 are regular regular languages. Then the right quotient of the language L1 with the language L2 is also regular. We shall say that the family of regular languages is closed on the right quotient with the regular language. Proof. That the language L1 is accepted by automaton capital, where automaton and capital has this set of state Q capital, our alphabets capital sigma with the transition function delta with the initial states Q0 and with the set of final states F capital, and this automaton is a deterministic finite automaton acceptor, sorry. We construct another deterministic finite acceptor M capital with hat with states with alphabet with transition function with initial state and with the final state F capital with hat in the following way. For each state Q or I, determine if there exists a word Y from language L2 such that delta star of QI Y is equal to QF, which belongs to a terminal state, set of terminal states. This can be done by looking at deterministic finite automatons M capital I with the set of state Q capital, our alphabet sigma with transition function delta, initial state QI, and final state the state of final state F. The automaton mi is m capital with the initial state q0 replaced by qi. Now we determine whether there exists a word y from the language accepted by automaton mi that is also in the language L2. For this, we can use the construction for the intersection of two regular languages given in theorem 4.1. Finding the transition graph for the intersection of the language L1 and language which is accepted by the automaton MI. If there is any path between its initial vertex and any final vertex, then the intersection of languages L1 and languages accepted by automaton MI is not empty. In that case, add qi to the set of states f capital with hat. Repeating this for every qi from the set of state q capital, we determine the set f capital star f capital with hat, and thereby construct the automaton m capital with hat. To prove that the language with accepted automaton m capital hat is equal the right quotient of the language L1 with the language L2, let x be any element of this quotient. Then there must be a word y from the language L2 such that x, the word xy belongs to the language L1. Please imply that the image of q0xy under the extended transition function delta star belongs to the set of final states f capital. So there must be a thumb state q so that the delta star of q0x is equal q, and delta star of qa belongs to the set of final states f capital. Therefore, by construction, q belongs to the set of final states f capital with hat, and automaton m capital with hat accepts the word x because delta star of q 0 x belongs to the set of final states f capital hat. Conversely, for any word accepted by automaton m capital with hat, we have that delta star of q0 of x is equal q belongs to the set of final states of automaton m capital with hat, f capital with hat. But again, by construction, this implies that there exists a word y from the language L2 such that delta star of qy belongs to the set of final state of automaton m. Therefore, the word xy belongs to the language L1, and the word x belongs to the right quotient of language L1 with the language L2. We therefore conclude that the set of the word is accepted by the automaton m capital with hat coincide with right quotient language or right quotient of language L1 with language L2, and from this that we get this language is regular. This complete our proof. Example. Find the right quotient of language L2 with the language L1 with the language L2 for the language L1. It consists of which is by the expression A star BB A star and L2 which is generated by the expression AB star. We first find that means finite acceptor that accepts the language L1. This is easy and a solution is given in the following figure. The example is simple enough so that we can skip the formality of the construction. On the graph in the previous figure, it is quote the evidence that L of M star intersects with L2 is the empty set. L of when 1 intersects L2 is a set it consists of one element A, and it is not empty. Similarly, we have the intersection L of M2 intersection L of 2, yeah, and as I say, and we have this language is accepted by Automata M3 intersection with the language L2 is an empty set. Therefore, the automaton accepting the right quotient of the language L1 with the language L2 is determined. The result is shown in the following figure. It accepts the language denoted by the regular expression of A star B plus A star B B A star, which can be simplified to A star B A star. Yeah. Therefore, we get that the right quotient of the language L1 with the language L2 is the language denoted by a regular expression A star B A star. So good, we finish our lecture. Thank you for your attention. I wish you good luck, good health, and the finish of the Russian war. Please send me your message that you listen my lecture on my mail. Thank you for your attention. Goodbye.